Hey, Honors Chemistry, it's April 2nd, Thursday. I'd like for you to turn in your books to page 513. On 513, you see a graph. Looks like this. Let me show it to you. Yep. And so the discussion is on 512, but what I want you to see is this. Going down the right-hand side of the graph, you go from carbon and oxygen and forming carbon dioxide, which is down here. You release 393.5 kilojoules. But in order to get back up to the carbon monoxide, from breaking down this, so decomposing that, to get it to carbon monoxide, would require that you input 283 kilojoules. So using Hess's concepts, you go from here to there, it's going to be add those two things together. Add these two steps together, that one and that one. Add the constituent elements to form carbon dioxide, and then break down the carbon dioxide to come back to carbon monoxide. And there are industrial processes that do that. And these two things, that green line and that green line, happen simultaneously. So it's hard for them to see the individual steps. They can see what they started with and they can see what they ended with, these two things, but they don't know how they got there. But they think, theoretically, that it forms this and then that decomposes to that. And so the answer is negative 110.5. When you subtract that minus that, get the difference, negative 110.5 kilojoules is the delta H, carbon and oxygen to form the standard states, the carbon monoxide. And that's what happens when you have a limited amount of oxygen. And it's kind of like a car when it drives with a bad tune-up. You get some carbon monoxide coming out of your tailpipe. You don't want that, because that's going to poison your blood if it happens to seep up through the floorboard of your car. Okay, so let's go take a look at a problem that would be an example of one you might see in college. And that would be, let's take number 31, page 524, number 31. Same concept as this right here. 524, number 31. So it's, you can see the graph there. When you're taking, let's see, what do we have on the top up there? Do we have tin and chlorine? And then what happens is they form tin 2 chloride. We know that's tin 2 because that's negative 1. There's 2 of them, so that's tin 2 chloride. And then we form tin 4 chloride. Okay, and so you release 325.1 kilojoules when this is formed. And then after that's formed, that combines with some more chlorine that happens to be in the container. And it forms this. And it releases 186.2 kilojoules. So those are the two steps in a two-step process. That's what we call it. And so if you look at the equations that they gave you, and that's what they'll do in the problem, they may not show you the picture, but they'll show you the equations there like that. And all you have to do is just add up the delta H's. Just add negative 325 to negative 186, and the answer will be negative 511.3. For a two-step process going from tin and chlorine and forming that product. So that's a real easy problem to solve if you know how to add. Number 32. Well, in case we don't have time, let's go ahead and do 523, number 16. Flip the page back to number 16. It's for glucose, C6H12O6. I'm always playing beat the clock. You know what that's like. We got an enthalpy of formation of negative 1263 per 1 mole. Calculate the enthalpy change when 1 mole of that combusts to form carbon dioxide and water vapor. We're going to burn that in oxygen, carbon dioxide, and liquid water. And you guys know they want the delta heat for the equation at standard temperature. All right, and so the heat of formation is 1263. If you're putting this together from its constituent elements, and we got this in the table, and we got that in the table for heats of formation, so we can use that equation. It's going to be this. You're going to take, well, we got to balance the equation. 6, 1, 12, 6 plus 2 is 8. So 12 plus 6 is 18. And there's 6 of them there, so there's like that. I think I already did this problem. Well, it bears repeating. So it's going to be products minus reactants, to use the shortcut formula, just like you did in your homework last night. And so it's 6 times, and we're going to go to R66. And it's going to say for carbon dioxide, negative 393.5. Plus 6 times, this is liquid water, hydrogen oxide, negative 285.8. And that is going to, then you're going to subtract the reactants, which is 1 times, they gave that to us in the problem. And that was 1260, negative 1263. Plus 6 times 0. And when you do all that math right there, let me look at the answer. You should get negative 2813 kilojoules. You don't say per mole, but you could. You could say it per mole of glucose because there's a 1 in front of glucose. But it's the enthalpy change of the reaction. That's what it is, not just of the combustion, because that's that could be considered combustion of glucose. Yes. All right, and then let's take a look at 524, number 32. 524, number 32, standard enthalpy of formation of sulfur dioxide gas is this. So that's enthalpy of formation. So what does it mean to make sulfur dioxide gas from its constituent elements? Well, it means you take sulfur and add it to oxygen, and you're going to get sulfur dioxide. I'm not even putting states of matter because I want to hurry along here. And the enthalpy of formation is negative 296.8. Kilojoules per mole. Okay. And so calculate the amount of energy given off in kilojoules when 30 grams of SO2 is formed. Well, we got 30 grams, and you always put it over here. Let's balance the equation. 1 sulfur, 1 sulfur. 2 oxygens, 2 oxygens. Okay, so it's going to be 1, 1, 1. So we're going to start with what they gave us, 30 grams of SO2. grams of SO2, moles of SO2. And so that's 32 on your periodic table, and that's 16 and 16, that's 32, that's 64 grams of SO2 is 1 mole of SO2. Boom, boom. And then 1 mole SO2, when it forms, releases 296.8 kilojoules. So moles cancel, and you multiply that times that and divide it by 64. And the answer is supposed to be 139.1, and I think you're going to get that. Kilojoules. And if this would have been an equation that had a big old fat 2 there, that would have made things different, wouldn't it? You'd have to go ahead and factor that in. Okay, so that's a good problem. And we've got 514.6a. 514.6a. Take a look at that, 514.6a. Do you see how they gave you the thermodynamic data? They didn't give you the picture, you know, the little graph thingy that has the lines coming down. They just gave you the equations. So this is all the grunt work that you did last night in your homework. You're going to have to take a look at those on number 6a. Do you see how on the top equation you have hydrogen and oxygen on the left? And on the bottommost equation, you have hydrogen on the left also. So that bottom equation has to be flipped around. And then the negative 224 is going to become positive 224. And that's going to put C8H18 on the left-hand side. And then that way it'll be where it's supposed to be for the what we call the target equation. And you can cancel out that way the hydrogen. And then that way the carbon will be on the right also. So that bottom equation, if it gets flipped, you're going to be able to cancel stuff out. And the middle equation added to the upper equation is 1.5 oxygens. And then somehow, that's going to be part of the original key target equation. So that's all you have to do. Maybe you're going to have to multiply them. You see 8 carbons on the bottom equation. And then there's only, well, you're going to have to balance the equation. Well, the equation's already balanced. Let's see, there's one, in the middle equation, there's only 1 carbon. So it's going to, the 80 carbons on the bottom equation, you're going to have to multiply the middle equation by 8. So then you're going to have to multiply that negative 393 times 8 also. So this number 6a is just shortening things up for you. So you don't have to think about it as much. But you still have to flip the bottom equation. You got to multiply the equations times the appropriate factor all the way across, and then subtract all of the enthalpies of heat, enthalpies of change. Okay, that's nice. So take a look at the MREs on page 515. That's rusting. In a rusting process, gives off all kinds of enthalpy of heat, of reaction, and the military put that to use to make battlefield meals called MREs, called meals ready to eat. And so you can read that if you'd like to. So see ya, and great. That's the end of Hess's law, by the way.